to understand what a wave is, first you have to understand oscillations. Now, oscillations, basically, there are many types of oscillations, but what we're going to look at and what you have to understand is what's called simple harmonic oscillations. So as you can see, you have these particles represented by the green and the red beads. They are connected together in the form of a string. And excuse me, at the other end, you can have it fixed, or you can have it loose, or you can have no end at all. But let's start with the fixed end. And if you manually move this wrench up and down, you see how the energy spreads out through the wave. And if I increase the frequency, frequency is the number of oscillations per second, you can see that the wave moves faster through that. You can see that. So already you see that waves are connected to the frequency. Now, oscillations, look at that. So if you let it oscillate, it's more regular. And this is a wave. So in a wave, you basically have particles that are moving up and down about the equilibrium position. Now that, what is that? The brown dotted line is basically the equilibrium position. And all the particles are having the same amplitude. Let me decrease the damping. All the particles have the same amplitude of 0.75 centimeter, but they are not synchronized. That means they are not oscillating in perfect unison. Now, in physics, this is called phase, Phase. So the amplitude of all these particles are the same, but they have a phase difference. Now, we can also say that phase is the state of vibration. So, that amplitude is right now, that displacement is zero. I should say the displacement is zero. For this green bead, the displacement is different. So each particle has a different displacement at a certain time. But when they all get to the amplitude positions, they have the same amplitude. It's only that they get to their amplitudes at different times. I hope that makes sense. You also have frequency, which you can change here. Let me make the frequency higher. You see, understand that the frequency is higher. Each particle is oscillating faster now. So the number of waves per second is also different. I can also change before I go there, wavelength is important, and wavelength is from one crest to the other. Let's get the first green bead is at 0. Let me move this ruler out. While that's the crest, the first green bead at 0 centimeter is the first crest. But when you go to 2.2 centimeter, you have the next crest, right? Just past 2.2. So the wavelength of this wave is 2.2 centimeter. You can either go from crest to crest, or you can go from trough to trough. Right now, I'm going from trough to trough. Again, you can see that the wavelength is 2.2 centimeter. So that is the basic idea of oscillations that you need to have. So let's get back to what we were doing, and then let's look at the important formulas connected with oscillations. The first one is the frequency of oscillations. And here I'm talking about a loaded light spring, as you can see. So you have a mass at one end of the spring, and that's the mass there, m kilograms. K is the spring constant of the spring, of course, or it's also called the force constant. It shows the tightness of the spring. So from this formula, you see the frequency of oscillation depends only on these two. And since K is in the numerator, a tighter spring means more frequency. while at the same time, a heavier mass attached means a lower frequency. I hope you're getting that. Don't forget the square root. So if I say that the spring constant is increased four times, the frequency only increases to two times. It only doubles because square root of 4 is 2. So that might be a conceptual question, okay? And again, the oscillating mass has both potential energy and kinetic energy. So this whole system, the spring mass system, and the total energy is given by 1/2 k a squared. Again, k is the force constant, a is the amplitude. And then finally, remember that the displacement y of each particle was different at a particular time. So you see the time there. So if you take time as 1 second, and then you want to find the displacement of a certain particle, you have to know its amplitude. Remember that all particles in this context have the same amplitude. So let's say the amplitude is like 3 centimeter, and then you have a cosine function. It could also be a sine function, right? We'll get to all those details later. But you see a new quantity called omega. The omega there is called the angular frequency, and it's related to the linear frequency by this formula. Omega is 2 pi times the linear frequency. And the reason is one oscillation is equal to one circular motion. See, that's why we get that 2 pi from. So one oscillation is equal to 2 pi radians, which means two oscillations equal to 4 pi radians. So that's the connection. And that's a very important quantity. Phi is the initial phase, and it could be 0. You can see in this diagram that if we started exactly when the particle was here, phi would be 0. If you start a little before, phi is negative, and then here it's positive. So phi shows the initial angle. Now, this quantity together is called the phase. So the displacement equation has the amplitude and the phase. Okay. And then we can use calculus and get to the velocity, which we will do. So that was just the introduction to oscillations, which I had to give you so you understand this chapter better as we move on. All right, so what is the wave? It's a disturbance that carries energy. So energy moves out through a medium, but the mass doesn't move out. So the mass or the particle just oscillates in place while energy keeps moving ahead. So as I've shown down here, and so that let's say those are the waves in an ocean, of course. But if you have water in a lake and you have a stone falling down somewhere here, hitting the lake, you see that the energy goes out in all directions like that. But the water molecules are all oscillating in their own position. See that? So the energy goes out, but the particles are oscillating in place. That's a mechanical wave. Now, you also have electromagnetic waves that can go through space, like radio, television broadcasting waves. Light is also an electromagnetic wave. So that's the second type of wave. And then you have matter waves, which are waves associated with all particles, like electrons and protons and all that. We'll be looking at electromagnetic waves in greater detail in another chapter when we learn light. But our primary focus is going to be on mechanical waves. So keep that in mind. And then sound is the best example, like water waves or seismic waves are also mechanical waves. So let's get on with it. Now, I've already discussed this. But I want to tell you that waves can be classified again basically into traveling waves, and the other one is called a standing wave. We'll look at that later on. A standing wave or a stationary wave. It's coming later on. So, right now, we're looking at what is called a transverse wave, I mean, a traveling wave, which is also called a progressive wave because it just progresses into the medium. Now, a traveling wave preserves its shape as it moves through space. So that's where we draw this, this is the representation of the shape of a wave, and it transfers energy from one point to another without net transport of matter. Here are the symbols that are important in connection with a wave. Lambda is the wavelength, which is, I've already told you, distance between successive crests or troughs. Is the amplitude, which is the maximum displacement from the equilibrium. Time period is the time for one oscillation in seconds. Frequency is the number of cycles per second, and the unit could either be 1/second or hertz. Now, Hertz is the name of the scientist Heinrich Hertz, who first produced electromagnetic waves. But you can also use 1/second, which is technically second raised to minus one. Here we have an important idea. The speed of any wave is the product of wavelength and frequency. It's so important that you really understand how we get it. Now, what is frequency? It's how many waves are produced in a second, right? So let's say there are 3 waves in a second. And what's wavelength? Wavelength is the length of one wave. So let's say that's 2 meters. So now you have, oh, where did that go? Okay, so I'll try that again. Oh, here it is. So now we have three waves, each having a length of 2 meters. And these 3 waves are produced in 1 second, right? So we have 3 waves in a second, and each wave is 2 meter long. So how much did it move out in 1 second? 6 meters. So the velocity or speed is 6 meters per second. So that's how we get that formula, and that's very important. Frequency multiplied by wavelength gives you the speed of a wave. Now, the same is demonstrated here in this diagram. You can see the amplitude, you can see the wavelength lambda. Of course, this is 2 times the amplitude. Well, there is positive amplitude, there's negative amplitude, because this is the equilibrium position. I'm going about this, in detail, because only if you understand all this will the chapter become easy. If you try to fly through all this, then you're going to struggle. So here's an example. I'm not going to read everything out. Very clear. The wavelength is given, the frequency is given, the wave speed is just the product. Can we move on, please? Okay. Now, progressive waves, or what's that? Traveling waves, can again be broken up into two: longitudinal and transverse. Now, the word longitudinal means lengthwise. So you can see this wave here. You have the energy going out along the x-axis. The particles are also oscillating about the x-axis. That's why it's called a longitudinal wave. But in the next one, which is called a transverse wave, energy is going about the x-axis, but the particles are vibrating about the y-axis. So the medium oscillates perpendicular to the propagation. That's a transverse wave. Example, waves on a string, electromagnetic waves. All electromagnetic waves are transverse. Now, longitudinal waves, sound waves in air. or pressure waves as shown here in a spring. They are both longitudinal waves. And it's easier to draw a transverse wave than to draw a longitudinal wave, because in a longitudinal wave, you have compressions where the particles are closer together. You see that? Compared to where the particles are further apart. That's harder to draw, but here you can see that this is a crest, which is a compression here, a trough, which is called a rarefaction. I know these words, but you got to know all this. All right. Okay. So here is the transverse wave that is shown at two different times. Uh, so this is the profile of a wave that is shown at 0 seconds by the dotted lines. And then 3 seconds, this is the profile. You can see that the wave has moved from 10 to 12 centimeters. So it has moved through 2 centimeters. See that? In 3 seconds. So you can calculate its speed. You can also calculate the wavelength from here. What's the wavelength? The wavelength is from 2 to 10. So it's 8 centimeter. So the wavelength is 8 centimeter. You have the speed, and you can figure out the frequency. So there are so many things you can do by looking at the profile of a wave. Again, the amplitude is 6 centimeter. You see that? The amplitude is 6 centimeter. So it's important to understand how to read these graphs. Next, we come to the mathematical model of a traveling wave. So y is the displacement. So y shows how much each particle is away from the equilibrium position. So for example, if you look at this particle, its y is 0 because it's at the equilibrium. But this particle is at the amplitude position at the same time. So remember that this particle is going up and down. The particle here is also going through the oscillation. And since their amplitudes are the same, it's doing that. But right now, when you take a snapshot, this particle is here, at the same time, this particle is here. Are you getting me? Okay. So if you look for y, well, this is y is a function of both x and t. So depending on x, so how far away it is from the origin. So that's the origin. If you look at this particle, that's the x of that particle. It'll have a particular y depending on its x position and the time. So y is a function of x and t, and it's either given by a sine function or a cosine function, because basically both of them have the same profile, the same shape. It's only the starting point that changes. Now, instead of taking x on the x-axis, you can also denote it by the angle. And you can see that this is 2 pi, which means it's a one oscillation, one wave. And then send the second wave. So you can see that x is replaced with that. So this is one lambda, isn't it? This is one wavelength, right? That's one wavelength. And one wavelength corresponds to 2 pi. That's where you get this. If you divide 2 pi by lambda, you get the wave number. It's called k. So k is 2 pi divided by the wavelength. So if the wavelength, let me write something, if the wavelength is 0.5 meter, then the wave number is 2 pi divided by 0.5, which is 4 pi, right? And the unit is going to be radians per meter. So smaller the wavelength, bigger the wave number. In a sense, it is actually showing you how many waves are there in a meter. That's what it's showing. right? Omega is 2 pi times the frequency, which I've explained before. Let's see what happens if you divide omega by k. Omega divided by k. Okay, what's omega? 2 pi times the frequency. And what's k? 2 pi divided by lambda. Now that lambda goes to the top. And then you see that the 2 pi's will cancel out. Oh, what do we have? We have the product of frequency and wavelength, which is what? Velocity. So there is the second important formula. Velocity can also be calculated using omega by k. So if you divide the wave number by the angular frequency, you will get the speed of the wave. Second important formula. Now, going back to this, you see that y as a function of x and t is given by a sine or a cosine, whatever, all of this. And you understand k is the wave number, omega is the angular frequency, x and t are the variables. This is the initial phase. In most cases, this initial phase will be taken as 0. Okay? So I hope you understand the mathematical model of a traveling wave now. Okay, so traveling waves, I think I have a simulation here. Let's see. Um, this is from a site called ophysics.com, which is what we're going to use to do our labs. The blue ball above is in simple harmonic motion. Imagine that this ball represents a particle in a solid material. If this particle is bonded to other particles near it, its motion will affect the motion of the other particles around it. So this is how waves propagate through a solid. In fact, waves can move faster through a solid. Why? Because the particles are closer together than in a liquid or a gas. So the slowest propagation would be in a gas, and the fastest would be in a solid. I hope seeing this gives you a much better idea of what a wave is. See, all the particles have the same amplitude, but at a particular time, they are in different states of vibration. And remember that the state of vibration is what is called a phase. So you have a transverse wave and a longitudinal wave. So what you see now down below is a longitudinal wave. See how the particles oscillate along the x-axis, and the energy is also moving along the x-axis. But for a transverse wave that you see on top, energy is moving along the x-axis, but particles are moving along the y-axis. Let us get to some math now. Now, from the equation for displacement, remember y as a function of x and t was given by a sine kx minus omega t plus pi naught, right? From that equation, simple calculus will give you the equation for transverse velocity of a point. So when you talk about velocity here, you're actually talking about the velocity of the particles moving up and down. Okay, that's why it's called the transverse velocity. We are not talking about the velocity with which the wave is moving forward. No, we're talking about the velocity of the particles. All right, and we do know that the velocity of the particles moving up and down becomes 0 at the amplitude positions, right? Think about it. Don't they have to stop before they start coming back down? Yeah. That's why we have this function. You know that a sine and a cosine function can become 0 and can also become maximum. You know that. Now, the calculus part should be easy. Dou y by dou t is minus a omega cosine, because when you take when you differentiate sine, you get a negative cosine. But then, because we're doing it with t, you will have to write omega out again. Remember that? That's why we have negative a omega and then the phase. But if you do this again, you will get acceleration, which is dou squared y by dou t squared. And since the differentiation of cosine leads to sine, you have the sign there, but that negative sign is carried over. And then once again, you have to write the omega, which makes the omega omega squared. See? So the acceleration, we're back to a sine function, while velocity is a cosine function. Immediately you recognize that displacement and acceleration are in phase. Why? Because both are sine functions. That means when displacement becomes maximum, so when the particle reaches its amplitude, displacement is maximum, right? Exactly at that point, the acceleration also becomes maximum. But since velocity is a cosine function, when it reaches the amplitude, the velocity is what? Zero. There you go. So displacement and acceleration become maximum and minimum together, while velocity is the opposite. Okay, so we've looked at this before, and we've looked at the transverse velocities. And here is a problem, simple problem. That's the velocity. And if you're given a problem saying, hey, this is the equation that represents the transverse wave, immediately you should be able to recognize and say, hey, that should be A. And that's amplitude. But since this is velocity, you can, let me write this again. I'm having to write this multiple times. Okay, kx minus omega t. And you see that there is no phi naught here, so I'm not writing that. So when you compare, you see the amplitude, you can see that k is 4 pi, omega is 20 pi. And then if you're asked to find the transverse velocity at x is equal to whatever, and t given, all you got to do is substitute the values of x and t here and do the calculations. Okay, first compute the phase, find the phase, which is this part. So that's what I've done. Kx minus omega t gives you that. You get negative 0.1 pi. Once you get that, then put it back and into this equation because you're asked to find the velocity. See that? So you got this. Now put it back into this equation and you have negative a omega cosine of that phase. Carefully put this into the calculator and you will get the answer as negative 1.194 meter per second. So the negative sign for velocity shows that the particle is moving down at that instant. Remember, there's an equilibrium position. The particle could either be going down from there or it could be going up from there. So a negative shows that it's going down from the equilibrium position. Now, is that clear enough now? Okay, what about another question for acceleration? Similar. I don't have to read this. Using the same wave and point xt as above, find the acceleration. Now, this is the formula for acceleration. We already got the phase, and then all you got to do is plug it into this formula because you have that sine of this whole thing. Okay, a omega square, sine of the whole thing. Do the calculation, and you would get the acceleration along the y-axis. Now, wherever I can go faster, I am trying to do it, but you can always pause or go back and look at it, but I have to keep moving, okay? Now, we are coming to another very important equation, and this is applicable to a string that is stretched like a guitar string. Everybody knows that if you adjust the tension in a guitar string, the frequency at which it plays is going to change. And that's because the speed of the wave changes. And also in a guitar, you have strings of different thicknesses, different radii, and we're going to define a new quantity called linear mass density, mu, and it's the mass of 1 meter. So if you take a guitar string and measure the mass of 1 meter of that string and put it in kilograms, you're going to get a very small number, right? Because 1 meters of that string would be a few grams, and then kilograms would be so small. So linear mass density. So this is the formula for velocity, square root of the tension by mu. Remember that tension is in newtons and mu is going to be in kilogram per meter. And so if you break this down, you are going to get a velocity for sure, because Newton is what? Force is mass times acceleration, isn't it? And divided by a kilogram again, divide by meter. So instead of putting divide by meter there, I can put that on top. So now we'll see what happens. The kilogram gets canceled, and you have you're left with meter square by second squared. And then you have a square root. So when you take that, you get meter per second. I was just trying to show you that um, dimensionally, this formula is correct. That's what I tried to show you. But you have to understand that at a higher tension, the waves move faster. And if it's a thinner string, thinner, like think about the thinnest string in a guitar, that's where the speed is higher. Okay. Once again, if you like quadruple the tension, the speed is only going to double. So that's what you understand from that formula. Now, this formula is only applicable to stretch the strings. But what about for sound waves moving through a gas? Now, I'm just introducing it here because I see it. It's square root of gamma p by rho. Now, from the first semester, you may or may not even remember that gamma is the ratio of the specific heats, Cp over Cv. P is the pressure, rho is the density. So when you look at sound waves traveling through a gas, you know that it's affected by the nature of the gas because it depends on its gamma, and it's also affected by the pressure and the density of the gas. Like if the gas is under high pressure, then you know that the particles are closer, right? That's why the speed is higher. See that? And again, if it's low density, the speed is higher. So in this diagram, I'm trying to show you what mu means. You can already see that since mu is the mass of 1 meter, to get the mass of any section, you just multiply mu with the length of that section, okay? That's what is shown in the diagram. So a simple question worked out here. A string under tension 100 Newton has linear density 0.020 kilogram per meter. What's the wave speed? Okay, 100 divided by 0.020, do the math, you get 70.7 meter per second. Okay, we have a simulation here. This is the simulation we're going to use for our first lab, but so I'm not going to go into details, but you can already see that you can adjust the tension and all that. See that? Oh, okay. So if I increase the tension, let's see what happens. Take it up. Okay. I've increased the tension. The speed of the wave must increase, right? So another thing that you note here is that for certain tensions, it's not even seeming to oscillate. See that? But now it's oscillating. And also, if you change the linear density, that also affects it. See? So in a lab, you look at how these factors affect the frequency. You can also change the frequency of oscillation, but you see, it's not responding to all frequencies either. So more about this in the lab. You're going to look at this carefully in the lab. So you will get it right there. Basically, we are interested in transferring energy, whether it's a radio wave or a sound wave. We want to take energy as fast as possible, as further away as possible. So that's why we're going to look at the energy transported in waves. What are the factors that affect the energy? Okay. First of all, we define a new quantity called energy density, which is the energy per unit length of the string. That's where the mu is coming in. The energy carried by 1 meter of a string. And we should know that it's proportional to the square of the amplitude. So while speed of the wave does not depend on the amplitude, the energy carried by a wave depends on the square of the amplitude. For a harmonic wave, which is what we've been looking at, this is the formula for power. Now, power is energy per second, okay? So remember that that's not energy alone, it's energy by time. So the energy carried in a string per second is given by 1/2 mu omega squared a squared velocity. So look at all the quantities. I'm sure you know all these quantities. Okay, it depends on the speed, depends on the square of the amplitude, square of the angular frequency, and depends on how thick the string is. All right, the diagram below should make it even more clear. Okay, so now here's the problem, just direct substitution. If the mu is given, speed is given, what's the average power? Now, this is taken from another example, so all the other quantities were given in that example, which is written down here. So if you have the amplitude, omega, mu, and the velocity, you just have to plug everything in and you would get the power uh, transmitted by this wave. And you get it as 0.316 joule per second or watts. So that's how you work it out. So that's the formula for energy, and that's how you calculate it. Now, in your formula sheet, you will have most of these equations, but conceptually, it's important to understand what they all depend on, what it means, and all that, because there will be conceptual questions on the exam. So now, waves can be reflected at a boundary, or it can just go through the boundary. So that's what I'm trying to show here. So when a wave encounters a boundary between two media, example strings of different density, like you have a thin string which suddenly becomes thick. So now the wave is going to have to be either reflected or transmitted, or sometimes both. Okay. So that's what it says. Part is reflected, part is transmitted. Now, fixed end, remember, if it's reflected at a fixed end, the returning wave is shifted by a phase of pi. That means it's inverted. Look at this. So you have the pulse going up there, but when it returns, it's coming back inverted. So fixed end. But if it's a free end, then you don't have that inversion. See, it's going up, and when it's returning, it's the same thing. Keep that in mind. And there are quantities called transmission coefficient and reflection coefficient. We're not going to look at that, and this is a term in electricity. What it says that it depends on how strong the boundary is or how weak it is. Okay. I think we have a simulation. let's go to that simulation, which will make it a little bit easier for you to recognize all this. Okay. So you see that pulse? If it's a free end, see how it's coming back. And let's change it to a fixed end. And you see that it's inverted. And then if you want to see the unreflected one, see, if it's also partly transmitted, that's what happens. Part of it is transmitted. And if it's a free end, again, see the transmitted part and the reflected. I thought this will, this few seconds help you, but you can play with this simulation, and there are a lot more simulations. If you go there and test that, you see the number of simulations there. Just use all that. For all this, you need what's called time. So when you superpose two sinusoidal waves, so two sine waves, you are going to get what's called a standing wave. So let me draw it, and because it's important. So you have one wave going out, and then it's reflected from here. And if it comes back, it's a reflection on its own. Then you have. I know this diagram is not going to look very neat. Oh no. So if you draw the reflected, something like this, actually here it had to be that. Okay, so you see what's happening. So if you have a train of waves going that way and a train of waves coming back at the same time, so you have both of them continuous to the left and to the right, then they're going to affect each other. And what happens to this particle here is that it doesn't move. But this particle here, it moves with the highest amplitude. So you have nodes and antinodes. So this type of a wave is called a standing wave. It looks like it's not going to be moving at all. It's called a standing wave, also called a stationary wave. So how do you get a standing wave? A standing wave is produced when a progressive wave moving in one direction is superimposed on its reflection. And when you have that, using the math, which I'm not going into in detail, this is the equation for a standing wave. So what's important is to recognize that you get 2A there, see? Because you see that this amplitude at the antinode is 2 times the amplitude of any one of the waves. That's how you get that 2A. But then you also have cosine delta phi by 2, which is the initial phase, and sine of the phase. Now, to make things easier, always take delta phi as 0, okay? I am going to anyways. So if you take the phase, initial phase as 0, then you're going to get cosine of 0 by 2. Cosine 0 is 1, right? So if cosine 0 is 1, then this simplifies to this vanishes and this whole thing vanishes. So then you have 2A sine kx minus omega t. That's a simplified version, which is only true when the initial phase is 0. But in this problem, it is not. Now, if it is not, then we use the whole thing, right? Let's use the whole thing. And you have the amplitude given. You have the phase difference between them. So when you say the initial phase here, it also means that the initial and the reflected waves are not completely in phase. Let's say that delta phi is pi. So then you're going to get pi by 2, which is 90 degrees. And cosine of pi by 2, cosine of 90, is 0. So when you get a factor 0 here, because you're multiplying with a 0, this whole thing is going to become 0. Did you understand that? I hope so. Wow, I moved this whole thing. Okay, so you're going to get pi by 2, and the whole thing becomes 0. That means there's no wave at all. So they cancel out. I can draw that and show it to you. So it's like you have a wave like that, which is superposed on exactly the opposite, like that. Difficult to draw it. So if you add these two, then you are going to get the resultant as no wave. Nothing. See? When you do the lab, you're going to see that. So that's what I mean by if this delta phi, the phase difference between the two waves is pi, you see that means they're opposite to each other. This point is exactly opposite to this. So phase difference is pi. And then when you put it in here, it's pi by 2. So everything becomes 0. So that is called complete cancellation. Isn't it interesting to know that noise cancellation headphones use this idea? So whatever noise is to be canceled out, not the music, but the outside noise, like the roar of the jet engine when you're in an aircraft and you want to listen to music. So, what the electronics does is it takes that noise and creates another wave which is completely out of phase by pi and then combines them together. And you know that when you combine those two waves, they cancel out. That is the whole idea of noise cancellation. I hope that makes sense. So, all of this looks theoretical, but it has a lot of practical applications. Now, whatever I showed you there in the previous one is what is done here again. So, look at that. So, you have two waves. These are the two waves, and you can see that the phase difference between them is delta phi, because this wave doesn't have that one, this one has. If you combine them, mathematically you add them, you are going to get this equation. So the the steps in between, I am not using that because then the video will become like 5 hours. Please use the textbook if you want to know how we go from that to this end product. So this is what we were discussing. A very important equation. It shows you that if the two are in phase, right? That means delta phi is 0. Then the amplitude becomes double. Okay, there you can see the how they separate out. So you have those two pulses coming in, they become like that, and then they become like this. They're moving away. So it's two pulses that is shown there. Okay, hope that makes sense. And if it did not, you have more examples here for you to see the blue wave and the red wave. Uh, and you see, if you combine them, you get this total wave because there's no phase difference between them. You know what's interesting here? Their amplitudes are the same, the phase is the same, no phase difference because there's no delta phi is 0. So when you add them up, what you're getting is this wave. This is called constructive interference or interference. Okay, constructive. So when they cancel out, it's called destructive. And when they add up, it's called constructive interference. Okay. So that's destructive interference here. Right now, you can see. Okay. Just look at the waves. See the phase difference? This one has no pi, but this one has a plus pi. So you see that this is totally opposite at each point. That's why they cancel out, and you don't have a wave at all. Energy is completely canceled out. And that is what is called a standing wave, right? Now, for our lab, what's important is to know that when you have these standing waves in a string, if the length of the string is given, uh, the length of the string is L, and oh, now I have to draw the diagram again. Oh, goodness. Oh, let me use this diagram, not this one. They did not give me a standing wave, so I have to draw it. Okay. So you have, let's have the equilibrium position. You have a standing wave. I'll try to make one waves. Almost. And then you have its reflection coming back, and then you have this is the standing wave. So the length of this string is given, and then n is the number of segments. And you see two segments here. That's one, and that's a second. See? And if you check it out, you can see that this is one wavelength, but in one wavelength, you have two segments. And this is the node, this is the antinode. See that? So from one antinode to the next antinode, from one node to the next node, the distance is one wavelength. Did you get that? From one node to the next node, I should correct myself. From one node to the next node, the distance is lambda by 2. Lambda by 2, right? From one node to the next node, the distance is lambda by 2. Same thing from one antinode to the next antinode, the distance is again half the wavelength. Okay. All that becomes important. That's where you get this formula from. See that? Just what I told you now. If I were to write it, if n is 1, because we are looking at one segment, right? We were looking at one segment, and that means n is 1. And in this equation, if you put n is 1, then you're going to get what? Oh, lambda is 2L. Isn't that what you get? Or the length is lambda by 2, which is what I was trying to tell you. Make sense? Okay. And then frequency is always velocity by wavelength, because we know this. Therefore, frequency is velocity by wavelength, and wavelength being 2 times the length. So I have substituted this here, and you get that formula. So you can apply the same thing in air columns, like, that there are stringed instruments when it comes to music, and then you also have wind instruments, like a flute or a trumpet, or an organ. So, all that air columns are vibrating, but we will look at that in greater greater detail in the next chapter. Right. Oh, ooh, we had the standing wave here. I wish I had seen that. I would not have had to draw it. Okay, so that's the standing wave that I was talking about. Look at how much better it is. Okay, so that's what I was talking about. The node to the next node and all that stuff. And the phase difference between the red and the blue wave is pi radians. That's a standing wave. Okay. And here to demonstrate what I was telling you, if the whole string vibrates as one segment, look at it. If the whole string, so this is a stretched string, node to node, because where it's tied to rigid supports, you can't have any oscillation. So surely these are two nodes. And then it's like a rubber band that you hold in your hand, stretch it. So your two hands are at these 2 points. And then somebody plucks the middle of the rubber band, lets it go, will not oscillate like that. Yeah. So that's n is 1 because it's one segment, and you can clearly see that half the wavelength is lambda. I've said that before. Okay, or lambda is 2 times. But if you make this oscillate in 2 segments, then you have this setup, and then you see that wavelength is just equal to the length. Okay. If you have 3, then similarly you have these relations. Lambda is 2 by 3 of the length. If you have 4, and so on. So these are called harmonics or overtones. Okay. So here, let's work out a simple question. We know these equations. And so if you're given the length of the string and the wave speed Can you find the first three harmonic frequencies? Yes, because we know this. Lambda is 2L by N. So all you got to do is, okay, just plug it in. 2 times the length by 1, you get 3.0. That's the first harmonic. It's also called the fundamental frequency when N is 1. And then once you get the wavelength, you know that the frequency is velocity by wavelength. So you get the fundamental frequency as 25 hertz. Similarly, for the second harmonic, 3 by 2, you're getting 2 times 1.5. Again, 3 by 2 is 1.5 is the wavelength, and then find the frequency. Did you notice that it's exactly double? Of course. And for the third one, it's going to be 3 times. So that's in the case of a string, okay? So what about the summary? Hmm. Mechanical waves transport energy, but not mass. So you have these key parameters here, and this is one relation. We had another one. I've not listed all the relations here and the summary. We had another one, and we have the equation for waves on a string. We had the equation for energy. And then finally, we looked at how we have different interference patterns, which gives standing waves. That is this chapter. I know it's taken some time, but remember that that's one whole chapter. That's the concept. Now, you can build on this by using the freely available OpenStax textbook, and I've also provided notes. These are this will be a starting point